question.
So, Fred and Barney are driving their little feet-powered cars at each other, playing a game of chicken, or pterodactyl as they called it back then. Thank you, Chris. Fred and Barney are at opposite ends of a 1 kilometer long drag strip in their matching race cars. Fred accelerates from rest toward Barney at a constant 2 meters per second. Barney travels toward Fred at a constant speed of 10 meters per second. How much time elapses until they collide? How long before they have to peel off and avoid collision? Now, you might think, okay, well, sort of reading that doesn't sound too hard. Does it? Oh, okay, maybe I'm wrong. Well, here's Fred over here. We'll call this side Fred. We'll call this guy Fred.
Other side.
Back to our regularly scheduled program. Fred, Barney. Now, Fred is moving positively. Barney is moving negatively. Okay? Just left and right kind of thing. All right. Now, the total distance between there and there is 1,000 meters, right? 1 kilometer. 1,000 meters. Okay. We want to know how much time elapses before they collide. When they collide, what is true?
It might not be.
Will it be halfway? Well, one is traveling at a constant speed, the other one is accelerating. It can't be, right? It can't be halfway. But what is true when they collide? And when I started the answer, you'll go, well, duh, but...
Crash.
Well, that's true, but what's true about their
They're going to do
position? What's true about their position? They have to be in the same place, right? They have to be in the same place when they collide. Okay, so when they collide, their positions are the same. And again, when you stop and you think about it, you go, well, of course. Now, does that mean that their displacements are the same? No, it doesn't. Right? It doesn't. So we got to handle that. Okay, so I think we're in good shape here. So what we're going to do then is we're going to figure out when Fred's position is equal to Barney's position, and then at what time does that occur? And that's how we're going to handle it, right? So Fred's position, and you guys have a whole page, right? Yeah, okay.
No, I don't.
You used to in the old days, not. Fred's position is equal to his displacement, because we're going to say that he's starting at position 0. We're going to say that's position 0, and we're going to say that's position 1,000. Does that make sense? Okay, and I'm going to write over here, I'm going to write Barney's, I don't know why I pronounced it that way, Barney's position is equal to, now, is it equal to his displacement? Like right now, what's his position? 1,000. So would you say that, and what's his displacement before we start? 0, right? So would you agree with me that the Barney's position is 1,000 minus his displacement? Does that make sense? His displacement at the start is 0, right? If he goes 100 to the left, then it's going to be a position of 900. Now we got to be careful with that 1,000 minus the displacement, right? Because really his displacement is actually what? Negative, right? So let's just be aware that maybe that negative might have to become positive. Okay? You know what I mean? Because the displacement is technically negative. So let's just be aware that we might have a problem. But I'm going to leave it like that for now. All right. So what is Fred's displacement? So I'm going to write position F, PF, position Fred. And that is equal to his displacement. And now Fred is the one that is accelerating from rest, right? So he's got an initial velocity of 0. Do we know his acceleration? We do. We don't know the time, though, but the time is what we have to make equal, right? So in other words, Fred's position is equal to the displacement of VIT plus 1/2 AT squared, which in this case, because the initial velocity is 0, is simply going to be 1/2 of his displacement sorry, 1/2 of his acceleration, which is 2 times t squared. In fact, Fred's position is half of 2, which is 1. Fred's position is simply t squared. Fred's position is equal to t squared. And again, we don't know the time. Okay, well, let's go over to the Barney side of the ledger. Barney's position, PB. Now, his position is 1,000 minus. Now, the displacement for Barney's traveling at a constant speed of v of 10 meters per second. So how far does he go in, say, 3 seconds? 10 times 3, right? So it's just velocity multiplied by time, is it not? Is it not just v times t? And so I'm going to go 1,000. Now here's where I got to watch that negative. It's 10, but it's to the left, so really it's just 1,000 minus 10t, right? Are we good with that? I put the negative there from the subtract because I didn't really include negative 10, but we know that's going to work out, right? Like in 1 second, he's going to go 10 meters to the left, and his position is going to be 909. That works, right? Okay. So when does the collision occur? When Fred's position is equal to Barney's position. When does that happen? Well, that happens when, oops, maybe I'll write it like this. When PF is equal to PB. And that is when t squared is equal to 1,000 minus, oops, 10t. Does that make sense? I'll just pause there for a second. Okay, so now it's a matter of solving for t. How do I solve that for t? Well, unfortunately, that is a t squared kind of thing, right? And so I'm going to have to write t squared. The minus 10t comes over and becomes plus 10t. The 1,000 comes over and becomes minus 1,000 equals 0. And guess what I've got? Quadratic equation. Everyone has just been hoping for.
Hey, it's working.
So how do I solve that? Well, I'm going to go back to my old friend, quadratic formula, minus b plus or minus square root b squared minus 4ac all over 2a. Minus b is going to be minus 1,000, or 1,000 plus or minus square root 1,000 squared minus 4 times a, which is 1, times c, which is, b is 10, right? What am I doing? Sure, I know the formula, I just can't put the numbers in. 10 plus or minus. I would have figured that out eventually. 10 squared minus 4ac. All right. All over 2 times a, which is just 2. So I think I end up with 10 plus or minus. 10 squared is 100. Oh, that doesn't make sense. Something's wrong there, right? Oh, yeah, that should be a negative 10 there, shouldn't it? Maybe I'll get my notes to do it right. And this 1,000 here has to be negative 2, doesn't it? Oh, man. Rough start to the day. 4 times a, which is 1 times minus 1,000. That's better. All right, so anyways, I got 10 squared is 100. I got minus 4. That's minus 4,000, right? So I get square root 4,100 all over 2. And I'm hoping you guys can work that out on your own. I get 27 or minus 37 seconds. Why do I get 2 answers?
The plus or minus plus.
Yeah, you gotta do the plus 1, you gotta do the minus 1. Now, because it's time, clearly which one can't work? The negative 37.
No, that one can't work.
Well, it does if you stop and you think about it, okay?
No, it doesn't. I don't
Well,
want to think about it. I don't want to think
no?
about it. No.
Because We just found out when the times are, when the positions are the same. Are Fred and Barney ever, when they collide, are at the same position? Is there any other time when they're at the same position? Fred starting from rest, Barney starting way over the other side, right? They're never in the same position, right? But the quadratic equation doesn't know that. All it knows is that Fred is accelerating at 2 meters per second, right? And Barney's traveling at a -10. So if you sort of go back in time, there is a place sort of nonsensical where they would be in the same position, but it doesn't exist. Okay? It just doesn't make sense. This is a mathematical thing here. This is like a parabola, but it doesn't exist for -t. So obviously, the answer is 27 seconds. Okay. So, but wasn't the question, is it how much time elapses? Yeah, it is. Could you figure out where they actually collide?
Yeah.
Pretty easy, right? Although you could either throw 27 into, t squared, right? 27 squared per time, because that's Fred's position. Okay, so I don't know, is that hard? A little bit. It's certainly, I think it makes sense, right? You just have to know how to sort of set it up. Okay. All right. I would like you to try example number 13. Now you've got, if you flip over, you've got a whole page, right? I would encourage you to use pencil. Okay? I'll read it for you. I'll read it for you, and I will tell you it's very similar. Okay? Jack is running at 6 meters per second to catch a bus. He sees it start to move when he's 20 meters away. If the bus accelerates at 1 meter per second squared, will Jack overtake it? In other words, will he catch the bus? And if so, how long will it take it? So this is a little bit different because in the first one, the vehicles were doing what? Going in opposite directions, going together, right? And this one, they're going in the same direction. And this one here, this guy, the one on the left, is going at 6 meters per second, and the bus is accelerating, right? Now, he has to catch him. Do you understand that the number of the time, if he does catch him, that time has to be less than 6 seconds? Do you know why? How come he has to catch him before 6 seconds? After 6 seconds, the bus is already going to be going 6, right? And if he can't run any faster than 6, if he hasn't caught it by then, it ain't going to happen, is it? Right? Because he can't go any faster than 6, and the next second the bus is going to go 7. So it has to happen within the 6 seconds. Okay? So I'm going to suggest you do this, exactly the same thing. Talk about, now, what do you think? Should we make Jack's position 0 and the bus plus 20? Right? Okay, so now I want you to think about position Jack and position bus. Give that a little try and see if you can do it. I'll give you a little nudge. Position Jack is simply his displacement because he's starting at 0. He's traveling at a constant speed, so is his position not simply v times t? Right? He's traveling at a constant speed, so his position is 6t to the right. The bus, its position is equal to 20 minus the displacement. Some people would say 20 plus the displacement with a negative displacement. So that's going to be 20 minus. Now the displacement here is, oh no, sorry, it's not minus, is it? It's not minus. How come it's not minus? It's all plus, that's right. It's plus. So it's acceleration of 1 meter per second squared, so that's going to be VIT plus 1/2 AT squared. 20 plus, initial velocity is 0, so 0 times t is 0. 1/2 a squared, or AT squared. So 1/2, his acceleration is 1. So that's simply going to be 20 plus 0.5 t squared. Okay, so let's keep going here. So I've got 6 plus or minus. Now I think I've got a bit of a problem here, don't I? Because I've got minus 4 times 0.5 is minus 2. Oh, yeah. Oh, do you mean this one, Nicole, in here?
No, I just want to.
Yeah, okay, you're right. Yes. Thanks. I did that twice now, didn't I? So I got 4 times 1/2 is 2 times 20 is minus 40. all over 1. So, and Chris and Adam, you guys really need to watch this. Yes, you do, because what happens when, does anyone know what the number is called under the square root? And it starts with a D. The discriminant. Very good, Troy.
There's no square root for negative.
When the discriminant is negative, it means, no, it doesn't mean 0.
It's not a real number.
You're right. The answer is not a real number. In fact, there's no solution in the real world. Okay? Mathematically, it would mean that the parabola would, in fact, not, I'm just guessing, would not cross the axis, right? That's what it means mathematically. What does it mean in Jack's world?
He doesn't get
It means he's walking. Okay? Only in his imagination will he catch the bus. In the world of imaginary numbers. Okay? He does not catch the bus at all. And now I'm going to tell you a story about my nerdy little nephew. So I was telling my brother that I was posting.
Your brother?
Why is that so odd?
You don't do.
You have a brother? That's it? You have a brother?
Sure.
You got a brother? Odd that you would think that.
Sometimes.
Anyways, I was telling my brother that I was taking my lessons and posting them to YouTube. So my nephew wanted to see, right? It was just happened to be the weekend after this, right? So I showed him the video of Jack doesn't catch the bus. So he watches the entire video. There's a little like 8, 9-year-old kid watching this nonsense, right? And he says to me, "Why did you call it Jack doesn't catch the bus? You gave away the answer right at the start." I don't even know what to say to that. Jack does not catch the bus. Okay? It's a negative value. What would happen, is there a possibility that there could be 2 times for this? Is there a possibility, like if Jack was running faster, is there a chance that there could be 2 times that he catches the bus? Adam's thinking. Go ahead.
What if the bus stops?
No, the bus continues.
Oh, it doesn't ever stop to pick up more people?
No, well, buses do, of course, yeah.
There is a stop sign.
No. It's just like a infinitely long highway, and Jack's just
Oh, no.
giving her. No, is there? But if he could run fast enough, right?
No.
Like, what if he was running at 7 meters per second?
Maybe.
He might catch. But would he ever be in the same position as the bus more than once? No? I'm just going to leave you with that. You think about that. I'm going to leave you with that. All right. I'm going to stop yapping.
Dead dog?
Yeah, maybe, Justin. We'll see. I'm going to assign you a whole bunch of problems here. Page 64, number 1 to 3.
I'll go with you.
Page 73. Now, here, people hate it when I do this. I go 33 to 70, but leave out the following. 50, 54, 55, 60, 67, 69. I know you're not going to do them all. Okay? I wasn't born yet. I know you're not going to do them all. That's fine. You should do enough, right, that you feel, yeah, I can do this on a test. I feel comfortable. I've practiced enough.
Yeah, but I can't. So
Okay? We still have to do vectors. Today's Wednesday. I'm going to say...
Let's go Friday. 3 weeks from Wednesday.
There's school this week.
Let you think and don't have 3 weeks.
If I had to estimate, I would say approximately next Wednesday.
No school. Oh, no.
No.
Somewhere in there.
No
A
school.
week today.
No school next Wednesday.
I just don't like to finish the project.
Bad luck.
I can't study that.
That's why you're going to study every day in class, man. And all you got to do is just sort of... You guys got to get out of that habit of studying only the night before. All right, I'll give you time to work.